Okay, let's start. So last session, I talked a little bit about public key cryptography, and let's just review the scenario that we had there. So the idea was that I'm Alice, and I have some sort of, let's say, email server or something, but I don't want to be online all the time. And I want everyone else to be able to send me messages. I don't want the protocol to be interactive. In order for them to send me messages, I shouldn't have to interact with them. And we saw that the way we solved this last time using El-Gamal was that we had two different keys. So I'm going to have a secret key. And I'm going to call my secret key actually D now. And there's going to be a public key. And in this session, I'm changing my notation, and I'm going to show the public key by E. Now you will see very soon why I'm using D and E here. Okay, and the idea is that I just announce E. I announce E, let's say, on my website. So this is the first step. Alice announces E or publishes E. And then everyone else should be able to send me messages by just knowing this public key E. And the reason I call it public is because everyone knows it. Right, so everyone else should just be able to send me messages, and only I should be able to decrypt those messages and see what the actual contents are. So all of these people are sending me some messages on the internet. Right, but the problem is that just as the previous case, the channel is not secure. So I also have an adversary, let's call her Eve, who can intercept all the messages that go through this channel. So any message that comes to Alice will also be seen by Eve. And of course, Eve also sees all the messages that Alice sends. So you can think of Eve as your government or your internet service provider, someone who has complete access to your internet connection and any message that you send them. Okay. So what are the requirements that we have here? We basically said that we want to encrypt using the public key, and we want to be able to decrypt using the secret key. That's why I'm going to use E and D here. So the public key is actually also the encryption key. It's the key that you need to encrypt the message. And then the secret key is also the decryption key. So that's why I call it D. So let's just go over the requirements really fast. So what do I need? I need to have two functions, just as before. I need to have an encryption function, and I need to have a decryption function. So I will have an encryption function. And as before, let me just call it ENC for encryption. It takes some key K, and given that key, it maps strings to strings. So basically, it takes a message and it encrypts it. Now, of course, I also need a decryption function. So I would say I also have a decryption function. Let's call it DEC for decryption. It also takes a key K as a parameter, and given a particular key, it maps strings to strings. Okay. But previously, like when I was using one-time pad, I would always use the same key. Now I'm going to use two different keys. So I don't always have one key. I always have what we call a key pair. So I always need to have something like this. I have a pair of keys. One of them is the encryption key or public key E, and this is public. And then I also have a decryption key or private key D, and this one is private. Okay. Now, what are the properties that I need? Just like the case of symmetric encryption when we were using the same key, I need to make sure that if I encrypt something and then I decrypt it, I get the original message back, right? So that's pretty obvious. So the first requirement is that for every message M that I might want to send, if I first encrypt M, and let's say that I'm encrypting it using this public key, the encryption key E. And then if I decrypt the result, and I decrypt using my decryption key or private key or secret key D, then I want to get the same message M. Right? So this is just saying that my encryption and decryption actually works. I don't lose the message. But I also need to provide some security. And what is the security requirement here? It's pretty obvious, right? So you just have to see what does Eve see in this scenario? And then you have to say that using the information that Eve can see, she should not be able to find any information about my original message. Okay, so what's happening here? First, Alice is announcing the encryption key E, and then let's say Carol wants to send a message to Alice. What does Carol do? She takes the message, so let's call it M, and this is a secret, and she just encrypts it. So what she sends to Alice is the result of encryption of M using the encryption key E, right? And when she sends this message, Eve is also seeing this message. Okay, and then Alice decrypts it. So the idea is that if Eve knows this key, the encryption key, and if she also knows one encrypted message, or maybe even a sequence of encrypted messages, she should not be able to find any information about the actual message without the encryption, so about M. So my security property, or let's say security requirements, my handwriting is terrible on this. I will rewrite this part later. So my security requirement is that if I have an adversary Eve who knows my public key and knows an encrypted message. So if the adversary knows, let's say E, this is the public key, and also my encrypted message. So the result of encrypting a message M using E. Then she should not be able to find any information about the actual message. Okay? They cannot find any information about M. And again, this is just like before. I'm not saying that they cannot find M. Oh, and I have to write M with the other color, sorry. M is supposed to be private. So again, I'm not saying that the adversary cannot find M itself. I'm saying it cannot find any information about M. So if, for example, the adversary can somehow say that my message was an even number or an odd number, even if they get one bit of information, that's not acceptable. They should not be able to rule out any of the messages, basically. Okay, but just to emphasize the point that the only things that are secret in our systems are the secret keys, I'm going to also say that the adversary knows the algorithms. So the adversary knows how we're doing encryption and decryption, because we talked about this before. We're not hiding our algorithms. We're just hiding our secret keys. Okay, that's my security requirements. Now, actually, in the last session, we saw one way of achieving this, and that was El-Gamal's protocol. And we saw that it was kind of a non-interactive variant of first doing Diffie-Hellman key exchange, and then after the key exchange using one-time path. But now we're going to see a completely different algorithm, a completely different encryption and decryption scheme. And this is the one that is actually used most often. This is RSA. it's named after the 3 people who invented it. So Rivest, Shamir, and Adelman. Now, what should I describe if I want to describe an encryption and decryption scheme to you? I have to tell you several things. I have to say how encryption works. I have to say how decryption works. And even maybe before that, I have to say how we generate our keys. Because we've seen that these 2 keys, they're not completely independent of each other, of course. Somehow there is a relationship between my decryption key and my encryption key. So I have to be able to also generate the keys in a way that everything works out. And we've already seen how we generate keys for El Gamal because it's the same as Diffie-Hellman. But okay, so what happens in RSA? The idea in RSA is that, again, I want to do all of my calculations modulo some number n. So let's say I have a number n. It's a natural number. And all calculations are modulo n. Now, just as before, I have to make sure that I choose my n to be large enough so that I can encode all the possible messages that I want to send. So if I want to send, I don't know, 10,000 possible messages, my n should definitely be larger than 10,000 so that I can have different values for my messages. But that's not generally a problem. Now, since all of my calculations are modulo n, I want to say that my encryption key E and my decryption key D are also numbers between 0 to n minus 1. Okay. So I'm going to say that my keys are between 0 to n minus 1. Now, at this point, I'm not really explaining the algorithm. I'm just giving a wish list, like what it is that I like to have. And then we will come back and actually achieve our wishes. Now, I want to have a very simple encryption. I'd like to say that if I want to encrypt some message M using my key E, I would like this to be a very simple function. So I like it to just be M raised to the power of E. So I want my encryption to be like this, of course, mod n. So I want to say that whenever I have a message and I want to encrypt it, I just take my key and I raise my message to the power of my key. And of course, I do all of the calculations modular. I want to have this kind of simple encryption. And then I actually want my decryption to be equally simple. Again, I'm bad at using these colors, it seems. I just forget all the time. Okay, so you know that the message is secret. Now, if I want to decrypt something, I'm going to, let's say, decrypt some other message, M prime, and I'm going to decrypt it using D. Now, I want my decryption to also be equally simple, and I want it to just be the same. I want to just take M and raise it to the power of D. Sorry, it was M prime here. Yeah, I just want to be able to take my M prime and raise it to the power of D. And of course, this is also mod. Okay, so this is my wish list. I like to have a very simple encryption and decryption algorithm. I basically want to say, whenever you want to encrypt something, raise it to the power of the encryption key. Whenever you want to decrypt it, raise it to the power of the decryption key. Right? Okay, so this is what I want to do. But of course, the problem is that I need to have this property. I need to be able to show that if I encrypt something and then I decrypt it, I'll get the original message. So I somehow need to choose my keys, my public key and private key, so that when I do the encryption and the decryption, I get my original message back. But how does that look like? So if I first do encryption on a message M, let's say using my encryption key, and then I decrypt the result using my decryption key. What is the result of this? So this is just the decryption using D. Well, the encryption of M was M to the power of E, right? And then in order to decrypt something, I just raise it to the power of D. So this would just be M to the power of ED. So if I have an encryption and decryption that looks like this, whenever I encrypt something and I decrypt it, I get M to the power of ED back. But of course, I want this to be the same as my original message M. So I need this to be equal to M. Right? Otherwise, my scheme is not working. So now the question is, how do I generate my keys? How do I generate two numbers, or actually three numbers, because I have to also generate my modulus N. So how do I generate three numbers, ED and N, such that for any message M, M to the power of ED is equal to M modulo N? That's the problem I have to solve. Okay. Now, this is actually pretty easy. So first of all, what happens if my N is a prime number? Let's say I just choose N as a very large prime number. What do I get? So this is my first question. What happens if N is prime? Well, this is what I want to have. I want to say that for every M, M to the power of ED is equal to M modulo N. But what does this mean? Well, let's divide both sides by M. This means that for every M, M to the power of ED minus 1 is 1. Right? And again, all the calculations are modulo N. But this goes back to Fermat's little theorem again. We've seen before that if I have any number, any non-zero number modulo N, and I raise it to the power of N minus 1, I would get 1 if N is a prime, right? So in this case, the only thing that I need is that I need this power here, ED minus 1, to be a multiple of N minus 1. Because I know that if I start with any number M and I raise it to the power of N minus 1, I get 1. So if I just choose this power so that it's a multiple of N minus 1, I'm just going through that cycle that I was talking about several times, and then I would also get 1. Right? So the idea is very simple now. Let's choose E and D such that ED minus 1, oh, actually, I'm going to write it the other way around, such that N minus 1 is a divisor of ED minus 1. Okay. If I do this, then I'm sure that everything else goes through. I'm sure that M to the power of ED would be equal to N. So I can encrypt and then I can decrypt and I can get the same value back. Okay, this was by Fermat's little theorem. Okay, but how do I actually find this? Like, how do I find E and D such that ED minus 1 is a multiple of N minus 1. Okay. If ED minus 1 is a multiple of N minus 1, what does that mean? It means that ED minus 1 is equal to 0 modulo N minus 1. Right? But I can just bring the 1 to the other side. So this just means that ED is equal to 1 modulo N minus 1. Okay, but now you see, this is something that we're very familiar with. It means that D has to be the modular multiplicative inverse of E. But now it's not the inverse modulo N, it's the inverse modulo N minus 1. Okay, so D is basically E minus 1 modulo N minus 1, or E inverse modulo N minus 1. And we saw in the last session how we can compute inverses. It's just the GCD algorithm. So how do I find an E and a D like this? Well, I just choose my E randomly, and then I compute its inverse, and I say that's D. But of course, if I choose E randomly, it might be that it doesn't have an inverse, because we saw that an inverse exists only if like D and N minus 1 are relatively prime. But if I chose one of my keys and I saw that it doesn't have an inverse, so what? I just ignore it, randomly choose another key, and I continue until I find the key that does have an inverse. Because the vast majority of the numbers are going to be co-prime to N minus 1. Well, not the vast majority. A lot of the numbers are going to be co-prime with N minus 1. So if I just pick randomly, there is a good chance that I pick a number that is co-prime and has an inverse. So I pick randomly, I try to compute the GCD and the inverse. If the GCD was not 1, I just pick another one. If the GCD was 1, I also find the inverse. And then I say the inverse is the other key. And it doesn't matter which key I pick and which key I say is the inverse, it's the same. I can pick my secret key and say that the public key is the inverse, or I can pick my public key and say the secret key is the inverse. Okay. So, but this is actually not how RSA works. So it's too soon for that. This scheme that we have right now, just using a prime number, it satisfies our basic requirements that if I just decrypt something that I encrypted, I get my original value back. But of course, we also had this security requirement, which was that an adversary who knows these values, an adversary who knows my decryption key, sorry, my encryption key and my encrypted message, and also the algorithms, should not be able to find any information. But do we have that here? So let's see what happens. What does Eve see? So if someone is sending, let's say Alice has announced her encryption key or her public key E, and let's say that she had generated it using this process before. And so she announces it. And of course, she has to also announce N, because everyone should know what the modulus is to do the calculations. So Eve actually sees E and N. And then when someone sends her a message, let's say Bob is sending Alice the message M. The way he encrypts it is that he just sends M to the power of E. So Eve also sees that. Eve is also seeing M to the power of E. Now, the question is whether Eve can find any information about M. And unfortunately, she can actually find M. Like not just some information about it, but it can be the entire message. Now, why is that? Well, let's just go through the same argument that we made here. What did we say about D and E? We said that D, which is supposed to be a secret, is just the modular multiplicative inverse of E, modulo n minus 1. So there's nothing that stops Eve from computing that. So Eve can simply say, okay, I know n, so I know n minus 1. So I can compute D. Very bad handwriting again. I have to keep here. Okay, D, I can compute D, which is E inverse modulo n minus 1. Right? And again, computing the inverse is just an extended Euclidean algorithm, super easy thing to do. And also the same thing that Alice did when she was generating the keys. So Eve now has the secret key D, the decryption key D, and then she can decrypt the messages just like Alice. Right? So Eve would just say, my message M, which was supposed to be a secret, is actually the result of decryption using D of the encrypted message M to the power of E. Right? Because this is again M to the power of ED, and we saw that M to the power of ED is just that. So yeah, that was a nice try, but it didn't work. Now, what is the problem here? The problem is that Eve could actually know how to compute the decryption key. And the reason she could compute that is actually quite subtle. It's because she knows n minus 1. So you see, when I was doing these calculations, I said that D has to be the modular multiplicative inverse of E modulo n minus 1. But n minus 1 is an easy number to compute if you have n. So I have to somehow make sure that this calculation, the calculation that creates the key, is done modulo some other number. And that other number should be something that is hard to find if you just have the number n. It cannot just be n minus 1. So this tells me that I should not choose my n to be a prime. If I choose my number n to be a prime, I can find keys such that the basic property that decryption undoes the encryption actually works, but I will not have any security. So let's choose my n in a different format. Okay. So let me just add another page here. And okay, this is our second attempt. We saw that choosing a prime number doesn't work. So let's just choose the next simplest thing. Let's just take two prime numbers and multiply them together. Okay, so to generate the keys, Alice chooses two large prime numbers. I'm going to call these prime numbers P and Q, and they're going to be secrets. Only Alice knows P and Q. And then she's going to set N to be P times Q. Okay, and sets N to be P times Q. And again, from the colors, you can tell that N is something that is going to be announced, but I'm going to keep P and Q secrets. Okay. Now, before I go forward, the assumption that I'm going to have is that if someone knows a number n, it's hard to factorize it. It's hard to find its prime factors. And especially if n is of this form. If n is of the form P times Q, where both P and Q are large prime numbers. And when I say large, again, in practice, I mean that there are thousands or maybe even millions of digits long. Okay, so no one knows a good algorithm for doing this. So our security is again going to be dependent on no one knows how to do this, so we assume it's not possible to do, right? But maybe someone in the future comes up with an algorithm and then this whole system will break. But my assumption for now is that if I have a number n, which is the multiplication of two really big prime numbers, there's no way to find those two big prime numbers. There's no way to factorize it. But of course, Alice knows them because Alice didn't just pick a random n. Alice actually picked two prime numbers and multiplied them to find n. So she knows which prime numbers she took. Okay. Now, again, I'm going to say that my E and D are chosen the same way. And I'm going to say that my encryption is just raise m to the power of E, and my decryption is to raise the message to the power of D, and I'm going to say all of my calculations are modulo n, so I'm keeping all of that the same. It's just that my n is not a prime number anymore. Now, let's see what happens. So again, I need this property. I need to find somehow or generate, let's say, two numbers, generate a number D for decryption. This is my decryption key, and another number E for encryption, such that for every message m to the power of ED should be equal to m. And this is modular. And again, m to the power of ED is just the result of first encrypting m and then decrypting it. Okay. But now I have to be a little bit more careful here. So if I want m to the power of ED to be equal to m modulo n, I cannot just use Fermat's little theorem anymore because my n is not a prime. Instead, I'm going to rely on something else, and I'm just going to show you the name, and you can just Google it later because I'm not going to prove this for you. It's called the Chinese remainder theorem. So basically, I'm going to use only a very specific part of this Chinese remainder theorem. And it's this: if m to the power of md is equal to m modulo n, okay, what does this mean? This means that if I divide this side by n, and if I divide this side also by n, they have the same remainders. Now, n is p times q. So if they have the same remainders when divided by n, they have to have the same remainders when divided by p and when divided by q. Right? So basically, what I need here is that I have to say for every message m to the power of ED is equal to m modulo p, and m to the power of ED is equal to m modulo q. And this is actually equivalent to the previous case. One side of it is trivial, the side that I just talked about. The other side is because of Chinese remainder theorem. Okay. Now, but what does this mean? If I have to have m to the power of ED equal to m modulo p, well, I just saw before that if I wanted to have that, I could just choose ED in a way that it's like a multiple of p minus 1. Sorry, ED minus 1 is a multiple of p minus 1. That's what I need. So let's actually go forward with this. So I have to say for every m to the power of ED is equal to m modulo p. That means that m to the power of ED minus 1 is equal to 1 modulo p. And also m to the power of ED minus 1 is equal to 1 modulo q. Okay. I'm actually lying to you a little bit here about what messages m I'm going to use, we will later see that I would actually like to use the messages that are co-prime to n. So I will never use a message m that has either p or q in its factorization. But that's pretty easy to avoid. Like if you create messages normally, it's very unlikely that you somehow magically find p and q. Finding p and q is a hard problem. Okay. But here, when I'm saying for every m, I'm assuming that m is co-prime to n, because otherwise very bad things can happen. Okay. So this is what I have here. So I know that for every one of my messages, if I compute m to the power of ed minus 1, the remainder should be 1 modulo both p and q. Okay. So now I can use Fermat's little theorem. I know that if this power that I'm using here is a multiple of p minus 1, then this equation definitely holds. And I also know that if the power is a multiple of q minus 1, then this equation definitely holds. So I just make sure that my power is a multiple of both p minus 1 and q minus 1. Okay. So this is the idea. We need, or we don't need to, but okay, this is what we do. It's sufficient. We make sure that our power, ed minus 1, is a multiple of both numbers, of both p minus 1 and q minus 1. Okay. What does it mean to say that a number is a multiple of two other numbers? Well, it has to be a multiple of their least common multiple, right? So basically, let's say I define L to be the least common multiple of p minus 1 and q minus 1. And what Alice has to do is that Alice chooses E and D. So E was public and D was private, such that ED minus 1 is a multiple of L. So such that L is a divisor of ED minus 1. That's what she needs to do. Now, again, to do this, we're going to basically do the same thing that we were doing in the failed case of a prime number. We're going to say that ED minus 1 is 0 modulo L, which means that ED is 1 modulo L, which just means that E is D inverse modulo L. Okay, so now my key generation is just like the previous case. I just take some random number D, but instead of doing the calculations modulo n minus 1, which I had before, now I have this number L, which is the least common multiple of p minus 1 and q minus 1, where p and q were my prime numbers. And I'm just doing these calculations modulo L. I have to make sure that E is D inverse modulo L. So I just pick a random D, I take its greatest common divisor with L, and I use the extended Euclidean algorithm. That gives me the inverse E. And if there is no inverse, I just pick another one. And I do this until I can generate D. Okay. Now, based on all this math that we did here, it's pretty obvious that we have this property. That if I encrypt something and I decrypt it, I get it back, right? But I had this before as well. What I care more about now is the security requirement. So let's now analyze it again from the point of view of Eve. So what does Eve see? So just as before, Eve sees everything that Alice broadcasts at the beginning. So at the beginning, Alice is going to say, if you want to send me a message, here's the encryption key that you should use, or the public key that you should use. And here's the modulus n that you should use. So everyone is seeing that. Eve is also saying that. So Eve sees E and N. And then let's say someone is sending a message to Alice. So let's say Carol is sending a message to Alice. Instead of actually sending M, she's going to raise M to the power of E. So she's going to send M to the power of E to Alice. And I'm going to assume that Eve sees that as well. Okay. So now Eve wants to find some information about M. But actually now, again, we get to the part where we are a bit more hand wavy. No one knows how to do this. No one knows how to find any information right now. Because previously, we had a way of finding D. We could say that our decryption key D is just the modular multiplicative inverse of E modulo n minus 1. But here, the problem is that my decryption key D is supposed to be the modular multiplicative inverse of E, but this is modulo that number L, right? So instead of n minus 1, now I need the inverse modulo L, but L was the least common multiple of P minus 1 and Q minus 1. But as Eve, I don't know P and Q, so I don't know P minus 1 and Q minus 1. So I hopefully don't have a way of finding their least common multiple somehow magically. Again, I can't give you a proof that this is impossible, but the assumption is that you would need to somehow factorize n. Of course, if you could factorize n and find P and Q, then you could compute this least common multiple, and then you could compute this inverse, and everything would work out. But if you cannot factorize n, I can't say mathematically that it's impossible to find any information about the message, but no one knows how to find any information. So that's our situation here. So as of now, with the algorithmic and cryptographic knowledge that we have until this day, Eve cannot find P or Q, and she cannot find L, which is the LCM of P minus 1 and Q minus 1. And because of that, she cannot find D. And because of that, she cannot find M. Okay. So that's our situation here. And so if I want to be very specific about it, this is the RSA assumption. And I say assumption because we don't have a proof for it, but it holds as far as we know until today. So the RSA assumption is that given these numbers, given E, N, and M to the power of E, so this was the encryption key, this was the modulus, this was the encrypted message. Given this information, one cannot find M. We cannot find our original message M, or to be more specific, we cannot find any information about it. Okay, again, the anticlimactic point is that I'm repeating this 1,000 times. We don't have a proof for this. We just don't know how to do it. And that's why RSA is not broken. If you somehow find an algorithm that can do this, then RSA would break. So the difference here is that when I was just using a prime number as my modulus, it was actually quite easy to break it. It was quite easy to compute this inverse, because I just knew that my decryption key is the inverse of my encryption key modulo some number that was also easy to compute. It was just n minus 1, right? But now in this case, my Decryption key is the inverse of my encryption key, also modulo some number, but that number is hard to compute. I don't know how to compute L. And because I don't know how to compute L, I can't find this inverse. But as you see, it's a hand-wavy argument because maybe someone can find an algorithm that finds the inverse without finding L, right? But we just don't have an algorithm like that. Okay, now I'm just going to set up the environment for our next session. In the next session, we're going to talk about digital signatures. So there is quite a difference there, and the difference is like this. So here, I had Alice on one side, and everyone wanted to send messages to Alice. So the idea was that Alice announces an encryption key, and anyone who wants to communicate with Alice can just encrypt their messages using this encryption key and send them to Alice, right? But only Alice could read the messages. Now, when it comes to digital signatures, we kind of want to have the opposite effect. We want to be able to say that only Alice can sign. So let's say I have a file or a message or any kind of digital object, and I want to make sure that Alice approves of it. So I want to say Alice can sign it, but I want to make sure that only Alice can sign. But on the other hand, I want to make sure that everyone else is able to verify the signature. So as you will see, we're kind of changing the roles. The idea is that here, everyone else is sending messages to Alice. When we will talk about digital signatures, Alice is kind of sending messages to everyone else. And the problem there is to prove that this message is actually coming from Alice. Here, the problem is that we have someone who's an eavesdropper who's trying to find out the message. But when we will talk about digital signatures later on, it's not about whether the message can be seen by someone else. It's fine if someone else sees the message. It's about whether we can prove that the message actually came from Alice and no one changed it. Okay. So as we will see in the next session, actually the solution is very similar, because just to give you some intuition before the end of this session, here we have two actions, and we have an action that everyone can do and an action that only Alice can do, right? So I have encryption, and I also have decryption. And encryption is something that everyone does. Decryption is something that only Alice can do, right? When it comes to signing, I will have a signature function or a signing function and a verification function. Now, I want only Alice to be able to sign, but I want everyone else to be able to verify. So I can just use my decryption as my signature, and I can use the encryption as the verification. But that's an idea that we will see in the next session. But for now, I just want to talk a little bit more about how this entire system would work. So if we have many different people there, so Alice, Bob, Carol, Dave, whatever, each one of them can generate their own keys, right? So Alice generates a key pair for herself, a secret key D and a public key E, and just announces her public key to everyone else. And Bob does the same thing, and so on. Now, if you want to send a message to someone, you have to first find their public key or their encryption key E, and then you encrypt the message using that person's public key. And then you send it to them, and you're sure that only they can read it. So you've probably seen this, like if you have nerdy friends, they send you emails and then they have an attachment that is their public key that you can use for encrypting the next messages. And of course, we all ignore that, but it's something you can do. Okay, great. I'll see you next week.